Good morning, guys. I hope nice weekends were had by all. Um, Brief refresher on where we left off. We have gone through all the material of Chapter 12. I want to look at a few more examples that I sort of skipped around and set aside out of Chapter 12. Because just to help show how things can tie together from Chapter 12 stuff, but also some of the previous stuff as well. Look at a few. Make sure that you've seen a few situations that show up on the homework, that might show up on the test, that could be done with this stuff that we might not have looked specifically at an example of that yet. As a reminder, our first test will start this week. It'll probably open up around Wednesday, Thursday. It depends a little bit on how lab ends up going. So actually, that's the main thing that I wanted to go ahead and ask about. We've been doing lab every other week. This is that week. So one of these days this week, we're going to meet up on campus to do 2 more labs. And the thing that I wanted to inquire was, last time we met on Thursday. Now, we don't specifically need to meet on Thursday this week because I know everyone's doesn't always. I know that summer schedules are not always super structured, so I'll assume for this holding pattern that this Thursday is a good day to meet. But if Thursday is not good for you at all, or even just not ideal, let me know. And I could see us doing Wednesday, Thursday, or Friday, just one of those days, depending on when is most convenient for the most people, so such that the most people can be there easily. And we might start at 11 instead of 10, since as a small group we're able to get through things pretty quickly.
So I'm going out of town on Wednesday.
Mm-hmm.
So Wednesday, Thursday, and Friday is not going to work for me this week for lab.
Hmm.
It was a totally last minute beach trip, but
Okay.
yeah.
Okay. Well, our options then are meet tomorrow or meet next week. I could see either hypothetically work. I know tomorrow's short notice, so if that's not a good idea for anybody, it is okay. Um,
I I don't know. I might be able to do tomorrow. It depends on what the doctor says because I'm supposed to work tomorrow, but if the doctor says that I can't lift heavy, then I'm not going to be able to work.
ah,
So,
okay. Um, Andrew, do you have any opinions about any of this information thus far?
I think I could do tomorrow, and I could do next week as well. I work on Wednesdays and Fridays, so
Okay.
but any other day is should be fine with me.
Okay, so from that information, we'll keep Thursday as our standard for the time being. We can keep Thursday as standard. So, Reagan, when might you have the information that you were saying you'd need before you can know for certain?
oh, I go to the doctor this afternoon.
Okay.
So, I'll know this afternoon.
I think I think this week would work a little better. Okay, strictly in terms of material being taught and reviewed at what time, I think I'd rather meet tomorrow than next week, just because if we meet tomorrow, that's good application of heat and thermo stuff, which can help serve as review for the test that'll open later this week. So if this is amenable to you guys, I think as of this moment, our holding pattern will be, I will, Reagan, if you could let me know when it's convenient for you. Based on that information, we can meet either tomorrow or next Thursday. So those will be the 2 days. That's the either or right now. Does that sound agreeable for the time being?
Yes, and I'll let you know by probably like 3 or 3:30 today.
Okay. Thank you for that, and sorry to. I hope things go smoothly. Sorry to introduce extra wrinkles into things. Okay. Okay, so current holding pattern is either tomorrow or next Thursday. We'll just see. And that should be fine. Sorry, my back itches in the one place I can't reach. Okay, so that is lab. That won't interfere much with test day then. So, lab. Today, I want to look at more unique examples from Chapter 12. The next day that we meet for class, I plan on setting aside as review time to go over, like, just to look over all the material from the past, I guess 3 weeks at this point, for the most part. Look over the test study materials, probably highlight some review questions, and then we'll probably have a day or two off of class time just being study hours, and then the test will open, and you can take it whenever it's convenient for you from when it opens through to next Monday. And once the test opens, I'll still be in here for class hours if you want to come in and talk about questions, or alternatively, we can reschedule to. I can meet with you individually during a different time of day. If your best test time is 5 p.m., we can talk in here if you have questions about it. So today, example questions. The next day we meet for class, review, study day, test will open, and we'll have that concluded by the start of next week. Let me know if there are any other issues or debates or problems with any of this information thus far. Whenever we meet for lab, the 2 labs in question, I don't have my notes in front of me. One of them is phase change, and I forgot which one I had lined up for the second one. I'll have to check my notes again, but it'll be on the laws of thermodynamics. Okay, so there's 2 examples within the notes that I have lined up that I want to look at now, because information about them will be useful, 1, for the homework sets, and 2, as studying for the impending test. If there's any other... Additionally, if you have any questions about things you've been studying or the homework questions, let me know, and I will focus on that instead. All right. Make sure that that's sharing correctly. So, 2 sort of hybrid examples that involve a lot of different concepts. First, and this relates kind of specifically to... let's just talk about the example. We've mentioned between this class and Physics 1500 that the purpose of friction is... the purpose of friction is to do work, take mechanical energy away from objects by slowing them down and turning it into thermal energy. And so as a result of that, whenever friction exists, everything involved in that particular force of friction tends to get warmer. And this is going to be kind of a very extreme example of that. A car is driving along, and all 4 of its tires suddenly pop. Maybe this is happening in the middle of an action movie. Once the tires pop, the car is going to be skidding across the ground just on its aluminum wheel wells. And it takes 30 meters of sliding for the car to come to a complete stop. So as soon as it pops and as soon as the aluminum is grinding against the ground, 30 minutes of sliding, we come to a complete stop. Force of friction between the ground and the wheel wells is 2,550 newtons. And we know that friction is going to be involved here. Friction is going to be the force that is taking the car, slowing it down, and all of the car's kinetic energy is going to end up is going to be taken away by friction, turned into thermal energy inside the road and also the aluminum wheel wells. So, our job here is to figure out by how much the wheel well's temperature is going to increase as a result of this. We can assume all work done by friction becomes heat in the wheels, and the aluminum wheel wells have a combined total mass, so all four wells added together, of 40 kilograms. So, the information we're given here, we know the wheel wells are made out of aluminum, so we can consult the properties of aluminum on some of our constant tables. We know the combined mass of all the aluminum present. We know the force of friction, and we know the distance that force is being applied over. Friction operates by doing work, and since we know the force of friction and the distance that force was applied, we can figure out the work that friction did. So this is my work for this one. I've got the example itself written off to the side as I show my work here. So, work equals force times displacement. If it's specifically the force of friction you're plugging in, you'll be figuring out the work that friction does as something slides and as friction is applied to that object. So, what we need to figure out is the work of friction. Friction is going to do work, take energy away from the car, and whenever friction does work, it turns it into heat. So, by finding the work friction does, we will find the heat that is added to the tires, to the wheel wells. So, the force of friction is 2,550. It's applied by a distance of 30 meters. Multiply those two numbers together, and friction will create 76,500 joules of thermal energy. So that is the amount of heat that will be added to the wheel wells. And that means that is going to be the value that we plug into Q equals MC delta T when we try to find the increase in temperature of the wheel wells from gaining that energy. Pardon me, sorry. So, Q is going to be the number we just found, 76,500. M, apologize for my handwriting here, the mass of all the aluminum combined is 40 kilograms. 40 kilograms, that is the entire mass of aluminum present. We're going to need the specific heat of aluminum, which is our invitation to check one of our previous tables to find the specific heat of aluminum. I've already done that. That value is 900. Again, these tables would be available to you on test. And then the last thing we're going to find is the change in temperature of the wheel wells, excuse me. So, delta T is the only thing to solve for. We don't actually know the original temperature or the final temperature, but we don't need them, strictly speaking, because we were just asked for the change in temperature. So, delta T, after we perform some algebra here, divide by 40, divide by 900, is going to be an increase of about 2.125 degrees Celsius, which is an increase that your hand would notice if you were to touch the wheel wells afterwards. 2 degrees Celsius would be about an increase of 5 Fahrenheit, I think. Close to 5 Fahrenheit. which is something that is discernible to the human. If a human is able to touch something that is 5 degrees warmer than them, you'd be able to tell. So, this is how friction ends up making everything warmer. Just takes thermal energy, adds it to things, and increases their temperature as a result. There are far more extreme cases of this. This car was actually probably moving pretty slow for the increase to only be 2 degrees Celsius, frankly. If the car was moving much faster, if it skid further, that temperature increase would also keep rising. Additionally, aluminum has a pretty high specific heat as far as most metals go. If the wheel wells had been made out of iron instead of aluminum, the increase probably would have been closer to 10 or 20 degrees Celsius just by being made out of iron. But iron doesn't make very good wheel wells because of how heavy it is. So, there's specifically a homework question I think is similar to this that I'll go ahead and try to highlight for you guys. So, I currently have the Chapter 12 homework on screen, and the very first question involves friction generating heat and adding that heat to something. This is specifically the friction between a skier and the ground. You're told the mass of the skier, coefficient of friction. Use that to figure out the force of friction. And you're then tasked to figure out how far this person would have to ski to melt a certain amount of snow. So the math for that one would kind of work a little inversely. You'd first need to find the heat needed to melt all the snow, then figure out, the distance that you'd have to slide in order for friction to do that much work. But very similar principle. All right. Whoops. I see what I did there. One sec. Rearranging my slides one more time. Oh, that didn't work. Okay. One additional example I want to show you, just to make sure that you've seen this, seen the principles applied to this kind of context. I've talked a bit about how you could consider the muscles, the structure of a human body to be like a machine, and we're going to do a little bit of math related to that now. The chart on the top of this particular slide is one that comes out of the textbook that all of our WebAssign questions come from. It's a textbook this course is based on. You just don't need it for the class because all the questions are on WebAssign. But since it's from the same book, WebAssign uses this information as well. So if it asks a similar question or something along these lines, it'll be using this data. It'll present this data to you to be able to use in the question. And this particular table shows the metabolic rate, which is to say in physics terms, it's the power output, the power requirement of the human body in various activities, various states of being. I care mostly about this last column right here. But we'll look at more the individual parts of it as well. The column on the left here lists, various activities of varying levels of severity. Arguably, the least intensive thing a human can do is sleep. And then, in order from there, light activity, moderate activity, heavy, and extreme activities, listing some examples of each. It then goes on to list the oxygen rate, the oxygen requirements of a human engaged in these particular things, the metabolic rate required for those activities in units of kilocalories per hour, and then the metabolic rate again, but in units of watts. And since we like watts in this class, this is the column that I'm using for this question. It's the data that we would use most often if it comes up in a homework question. And like with commercial electronics, the wattage, the watt requirement, tells you how much energy the body needs in a certain amount of time to be able to perform that specific task. So, for example, if your metabolic rate when sleeping is 80 watts, that means that your body needs 80 joules or uses up 80 joules every single second. And then light activity, which I would just consider being awake for the most part, has a rate of 230 watts. So every single second, you need 230 joules of energy in order to stay awake. If your body does not have that energy, you will either, 1, be incredibly hungry, or 2, you will fall asleep. And then every single different category from there cranks things up accordingly based on the severity. So moderate takes up about twice as much energy, and then heavy about twice as much more, extreme twice as much more. And so these numbers will be different depending on the human. For example, this is based on a 65 kilogram male, which so these numbers do fluctuate. They fluctuate depending on who the person is, various details about them that they have little control over. But it's just a rough sort of guideline, that we're going to use in relationship to this question here. We're going to kind of treat the human body as a machine, and using how efficient the human machine is, try to figure out a few things about the relationship between your food and your activity level. One jelly donut contains approximately 1 megajoule of energy. If you look up the calories on food, I'm assuming that most of my students are some combination of bio and chem, so this is probably not new information for you. The calorie listing on all food packaging, metrically speaking, is actually kilocalories. So if it says, 200 calories per donut, that's actually 200,000 little c calories per donut. And when you convert calories into joules, that would be about 1 megajoule, because it's, I believe, about 1 calorie to about 4 joules. 1 little c calorie to about 4 joules. So food packaging is listed in kilocalories. We're using joules, so we've converted the donut into megajoules. Donut has 1 megajoule of energy inside of it, and that's in all of its chemical bonds. That's just the net amount of energy consumed there. If the body is 20% efficient in regards to turning eaten energy into available mechanical energy for work, then our first question is, how much available energy do we get per donut? When you eat a donut, how much of this amount, this 1 megajoule, actually goes into your muscles to be used specifically for work tasks? And then 2, how long, depending on your activity level, does it take to use that amount of energy? So, first question. Human body is about 20% mechanically efficient. That means that 80% of what you eat goes into other processes like making heat to keep yourself warm, keeping your brain functional, a bunch of other things that take energy that I'm actually not familiar with because, again, that's not my specialty. That just means only 20% goes into your muscles, and that's the only 20% that this course is able to do much with. So, first thing, we know the efficient. If we use the 20% mechanical efficiency as our nth value, and we put 1 million joules into the body, that's 1 megajoule converts to 1 million joules. What is the possible output per donut? So 20% of 1 million is about 200,000 joules. So that is the amount of energy that the one donut lets you start using. And then, next question, how much light activity and how much heavy activity does it take to use that amount of energy? How quickly will that energy be gone and depleted depending on your activity level? So, we have looked at this formula somewhat since starting this course. Power equals energy over time. Watts is joules over seconds. It's the rate at which energy gets used. So the more elevated states of activity level, you are just using more energy every single second. So power equals energy over time. We're going to take our different power ratings for our different activity levels and figure out how many seconds that one donut lasts. So, first option, light activity. Light activity for this particular human has a power rating of 230 watts. So that's using 230 joules every single second. So that power rating will go here for P. And we're trying to figure out how long it takes to use 200,000 joules of energy at this particular rating. So T is our remaining variable. So that one donut will last us 800 and approximately 70 seconds of light activity. For a sense of scale, 870 converted to minutes is about 14 and a half minutes. And light activity is basically just being awake. If you are awake and moving at all, list dressing, walking slowly, doing desk work, so moving your limbs in any way, shape, or form, you're doing light activity, and that donut will power your body. That one donut will power that activity for about 15 minutes. We are also asked to look at heavy activity. The power rating for heavy activity for this particular human is 700 joules per second, 700 watts. That's a rating that's about 3 times greater than the resting one. And as a result, the energy is used up about 3 times faster, 285 seconds. Which, just to double check my work real quick, 285.7 divided by 60 is about 5 minutes. So, the things that I'd like you to take away from this example are, 1, to show you how this math is utilized in relationship to the human body, because there's going to be a few examples and homework questions that utilize just these the basic principles of efficiency and the formula for power. 2, the difference between light activity and heavy activity isn't actually that great. Like, you'll use energy about 3 times faster is the difference between just being awake and playing basketball. So it doesn't really matter what your activity of choice is. If you're doing anything, you're awake and you're using your metabolic processes. And lastly, doesn't matter what you're doing, the one donut, you use the energy up from that one donut pretty quickly. So eat donuts. they're delicious, and they'll power your muscles for a little while. It's all good. All right. So that is all of the individual formulas and concepts from Chapter 12 applied in some way, shape, or form. At this particular time, one, I'd like to know if you have literally any questions at all. Any thoughts, needs, opinions, feelings, concerns about anything we just talked about or anything from Chapter 12. Excuse me. If there's no immediate questions right at this particular time, then I will call our usual session break. I'll be here for the next, I guess, hour and a half. If you jump back in with questions, I recommend you take a quick break, get some water and a snack, and spend the next little while looking over the homework. Make sure that you're comprehending all the ways the homework questions work, looking over them, making sure they make sense. And I'll be here helping out if you jump back in. Tomorrow, we will either meet for lab or we'll have a review day. I will send out an email confirming that with you as soon as I have the information. No rush, no pressure. But we'll try to coordinate everyone and make sure we are on the same page as soon as we can. Whenever we meet next for class, whether it's tomorrow or Wednesday, will be a review day. We'll summarize everything from the past 3 weeks and look over some of the test prep materials, make sure that everyone has seen them and is comfortable with them before the test opens. We'll then have another kind of study-free day after that before the test opens, and the test will be open by the tail end of the week for you to work on at your leisure. I'm kind of rambling at this point because that's what I always do. Any questions, please let me know. But if you don't have any right now, I'll be here for the next hour and a half for you to jump back in. Do be looking over your homework and your notes. And if you don't jump back in now, then I'll see you tomorrow.